Just wait for a minute. I'm unable to operate the iPad. Maybe some glitches. Just wait for 2-3 more minutes. I'm figuring out like wait for 2 minutes. I'm rejoining. Maybe some issues there. Am I audible?
Yes, ma'am. Yes.
I'm so sorry. Wait a second. I'm just turning on. Coming from the iPad. I think last lecture, Nilanjan, you were not there.
Yes, ma'am.
Have you seen the recorded video?
No, ma'am, I have not got the time. Actually, I was unwell.
Okay. It's fine. So last time we have done classless addressing.
Oh, okay. Yeah, I will watch the recording.
Okay. I think now it's fine. Sorry for the delay. So let's start with the week 10. You have asked for the extra session as well of the 2 hours. The mail will be sent to you when will be the extra session, like on which date. I have asked for 2 hours lecture, so that mail will be sent to you in like I think within a week. They'll inform you about that. Okay, so last time we have done classless addressing. So am I audible in the first place? My screen is visible now. Everything is fine. Okay, so let's start. Last time we have covered the addressing techniques and all. So today we'll complete that thing, and also we'll go to the QOS, that is quality of service, that we'll complete today. I'll make sure that at least these two topics are completed so that we can, in the next session, complete the routing part and then data link layer in the 12th class. And then after that, last class, maybe the somewhat whatever the syllabus will be left, extra class. And moreover, I'll focus on the revision thing. So just a gist of everything what we have done and the doubt session as well. So I hope so the thing should go like this only, because other like we are lagging behind already. So let's start with NAT. So last time we have covered many questions also, like gate previous year questions of classless addressing and all. Any doubts with that? I hope so it's clear. So let's proceed. If you have any doubt, please write in the chat. Okay. So there are many issues with IPv4 addressing as well. So we have learned how what was the addressing techniques, the classful addressing, classless addressing. Today we'll study about the NAT and IPv6 as well. And what was the issue there? Like what are the issues there? Let's try to learn about that. Any idea what can be the issues with the IPv4 addressing? First thing is it's very limited, the addressing. Why it's limited? Because we learned about the classes as well, like class A, B, C, D, E, D, and E. They are reserved classes. We learned only A, B, and C we can use. And why we switched from classful to classless? In the first place, the classful was basically having the fixed number of bits. And there was so much of wastage there. Either the space was wasted, or either the space was not enough. So that's why we switched to classless addressing, to have the flexibility, so that we can combine or break them. And then we learned about the subnetting as well as supernetting also. But there also we had that, okay, we learned that there are broadcast addressing, network addressing, network addresses which cannot be assigned to host. Further, there was a limitation there. The time when this IPv4 addressing was, the addressing technique was there, at that time there were not so many of the devices there at or one cannot think of so many devices can be in the future. Like, they were desktop computers only. So they thought that this much of addresses are basically sufficient, as there are there are a huge amount of addressing. But with the time, as we know that how many of like everyone is having so many devices in their home itself, everyone is operating so many of devices. So uh, they were not they haven't thought also that this internet, the devices will be mobile in nature. At that time, mobile phone was also not invented. Only desktop computers were there. So mobility itself is also not there in IPv4. If I say, the first thing is the limited amount of addressing. The second thing is mobility is not there. Now what is the solution? One of the solution here is NAT, network address translation. Any idea about NAT? Yes. Yes, come on.
The NAT is used for mapping the private IP into the public IP while it is leaving that particular area or zone.
So basically, private and public IP comes into picture. Why it comes into picture? Because to have more number of IP addresses, let's your main idea is correct. Let's see how it happens and all. So as we saw that, okay, there was a limitation that because the large number of addresses are unutilized here, class D and E, or we have lesser number of addresses being used addressing as being there. So what was the solution for that? The solution was the NAT thing, or I can say make the address reusable. I'll tell you about how it is connected with NAT. So what I'm trying to say, make the same address we can use the same address again. How we can use it? Like suppose if I talk about globally, obviously globally, if I have to differentiate about like someone wants to approach me, Prableen, so obviously there is not one Prableen in all over the world, or there can be many Prableen there in the world. But if I talk about IIT Tirupati, it's easier to identify me, and maybe there can be one more than one Prableen. Then if I talk about IIT Tirupati CSC, obviously, like again, there is less probability that there are more than one Prableen there. So that is how we basically disambiguate. Or I'll further explain you what I mean to say. I'll this is just a layman example. What I'm trying to say that globally, we have what it means is globally we should have the unique address. Whereas if I talk about privately, I can have within an organization I can reuse the address. This is what I meant it to be. So basically, what they are trying to say, we can have private addresses as well as the public addresses. That is what I said. Private, obviously, there are lesser chances to have the with the same name within an organization or within the department. So we can reuse the address, reusable, and public address, they are non-reusable. Now, one more thing, I'll dive into the public address and a private address also. So suppose if I want to send, if the source wants to send something, it has some private IP. So it will, when it is sending to the destination, it will select from the pool of public IP and send it. Can someone elaborate what I'm trying to say? Maybe I haven't said it clearly. I know maybe some vague explanation is there. I'll furthermore dig into it. Can someone try to explain what I'm trying to say here? Yes, come on.
Ma'am, the source private IP is converted into a public facing IP, and then that public facing IP is used for transmitting it to the destination, transmitting the information to the destination.
Yes, absolutely. So what I'm trying to say, I'll again come to above example. Don't worry about that. I'll just show you the same example which was shown in the presentation itself. Suppose the source IP is 10.0.1.2 and the destination IP is 213.168.112.3. And suppose the private addresses, now the source same thing, 10.0.1.2, and the public addresses 128.143.71.21. So what I mean to say is and this is NAT, network address translation. Now what I'm trying to say is this is the private IP address. This is the source IP. This is the private address. When I'm trying to send it, I will map it to one of the public address. Every machine, basically, it is having one private address. And there is a pool of public addresses from which it will select it. It will map this private address to the public address, and then it will send to the destination. Now, for the destination, this was the source thing. Now, for the destination part, the sources. Can you tell me what is the source here?
Ma'am, 213.168, that
Yes.
thing.
No, source. From where it is coming?
Ma'am, at the destination, that should be the thing.
Okay. Yes, you are correct. You are correct if I'm sending it from here. But what is the source from where it has got? I'm saying.
That the previous one, 10.0.
No. Now it's not 10.0. It's basically 128.143.71.21.
Oh, yes.
Why it's that? Can you explain?
No, because that's what the destination sees, the public address.
Yes. I hope so. Now I'm getting much clearer. Like if my source was this is my private address. This private address is not known to the destination at all. What is known to the destination? Public address. Private address is mapped to the public address. Now I'll tell you why we are mapping also. And then that public address is the destination knows that this was the source. It doesn't know that this was the source. For destination, private IP is it doesn't know at all that what was the private IP address. And destination, obviously, it is the same what has received. Now, if destination is sending something, here a NAT table is maintained. NAT table basically maps public IP address, private to public and public to private. So here the destination is there. For the destination, now destination is sending to the source. Now the destination itself is the source. So I can say this 213.168.112.3. Now what is the destination? If this second one is sending to the above one, this first one. Can you tell me what is the destination IP address? Any one of you?
Ma'am, the public address.
Yes, the public address. What about others? Am I making sense? Nothing. It's simple only. What I'm trying to do, there is a private IP address and there is a destination I want to send. This source, this is a private IP address. Now, what is the use of NAT? NAT basically maps this private IP to the public IP. Now, this public IP is... Please mute yourself if you don't have any doubt. Now, this for the destination, this public IP is basically the source address, not the private IP. Destination is unaware of the private IP address. Now, why we are mapping? What is the advantage of that? Can anyone tell me? Why we are having a pool of public addresses, mapping private IP address to the public IP address? One of you told me that, okay, ma'am, here what we are doing is we are mapping. You told me the whole procedure. Now, can you tell me how we are avoiding the wastage of IP addresses from that?
Madam, my understanding is, most of the time within an organization, the network traffic is within the organization. Okay. So very less traffic goes to outside. So for which actually one address is public address is okay. So only when we want to send outside mails, then only we use that public address. Rather than, for example, we have 10 machines within a company. So let's say 100 machines. Instead of having 100 unique IP addresses from internet, it's a waste of resources. Since we rarely go outside our company's domain. So
I can say you are partially correct, partially incorrect, because you usually search google.com, you usually search you are doing the things which are outside, you are contacting the outside the organization as well. We can't say that we are having the internet within an organization or within our area only. We are contacting out, yes, maybe in one sense, yes, but in other sense we are very frequently also, I can say, contacting outside outside the organization also. I'll tell you the reason. Partially you are correct. How? I'll tell you the reason. Now, what I'm saying is, every machine has one private address, IP address. Okay, that's fine. But as you said, as you told me, we don't need that many of public addresses. You are correct in that part, that we don't need that many of public addresses. Why we don't need that many of public addresses? Because we can't say that, okay, every machine is having this unique private address, but all machines, they are not accessing the internet at the same time. Like, everyone is not accessing the internet. If I'm having 100 users, or I'll say 10,000 students are there in the organization, 10,000 will not operate the internet at the same time. So that's why we have small set of public address. And whenever a device wants to connect outside, they'll take from the pool of this public address, map it. NAT will map this private IP to the public IP, and then it will be sent. Is it clear? Does it make sense?
Yes, ma'am.
Yes.
Ma'am, does these also have some security concern with the private and public IP?
I'll come to that. Masquerading and all. I'll come to that. So,
Madam,
yes.
one more issue. Like, for example, let us assume hypothetically, like all the machines have public IP address only. Let us say all 100 machines within an organization has a public IP address only. And the problem comes every time for all messages inside the company, it goes to the outside for internet router, external internet router for routing, rather than confining the traffic to within the company. That's also a problem. Security.
Please, can you yourself, don't have any doubt? Someone is asking the doubt. Please mute yourself. Yes. Continue. Yes, what you were saying.
Yeah, what I'm saying is, let's say an organization has 100 machines, and hypothetically, let us assume all the 100 machines obtained a public IP address by paying money to internet register, a public IP address. Okay. The problem is that for the traffic within the company also, it has to go through external router because it's public IP address. So that is a wastage of bandwidth. If it is
Yes,
private
yes.
address within the company.
We don't need that much of public IP addresses. That is what I'm trying to say. To save that IP addresses, to save that pool of IP addresses, that is why we are having private IP addresses. You are correct in that way. That is why we don't need you are correct here, that we don't need that much of IP addresses, public IP addresses.
See, another thing, madam, assume hypothetically we don't want to connect outside. For example, I've seen North Korea. There is no
yes, and that's
everything within the country itself.
Yes,
they don't even require
no need of public IP addresses.
Yeah. Okay, madam.
And the other person who was asking the doubt, you were saying there can be security issues. Can I say that it's good, rather than security issues, it is providing security, because private IP address is not visible to the other person, to the destination.
Nilanjan, yes. It doesn't go out. Those packets won't go out.
Nilanjan, can you tell me is it clear?
Yes, ma'am.
Like you are saying, you're confused. Is it
No, ma'am. Actually, I was getting confused in the conversation, not the concept. No, it's now clear.
Yes. Oh, now it's now clear. Okay. So rather than I can say that it's I'll not say it's a security solution, but it can provide a certain level of security, as you have asked me, because we private IP address is not visible to the destination. Can I say in one sense that? So though I was going to come further, okay, it's fine now. This was the basic operation of NAT, how it works basically. So every machine basically it is having one private IP address. We don't need that much of public IP address as per the like we have also discussed, and we have like NAT box here. It is managing the pool of public IP addresses, and it selects one of the IP addresses from the pool. I can say and forward the packet from that IP. So NAT has multiple use cases. One of the use cases this. The other use case is migration between ISPs. Can someone tell me how migration between ISPs? How NAT can be helpful within this? Okay, NAT is basically public IP, private IP we are having. That is fine, but how it is, how it's helping in migration between network service providers?
So in this case, ma'am, we can just change the configs in the NAT box. Just change the public IP mappings because the private won't be affected.
Yes, absolutely correct, Aman. Like we can change the public IP address, but why we need to change when we are connecting? Like, okay, as you said me that, okay, this is one device. Like here, this is the NAT thing. Sorry. This is the NAT thing. This is ISP1. This is ISP2. And here, suppose there was a failure. And now, as you told me, okay, here I have to change. Earlier, the source was different. Now the source, I have to change it. Now the public address, I have to change. This is the main thing, which you are also saying. Public IP address have to change, and private IP address, no need to change it. So it's better. But why, when we are have you got this question in your mind, like why we have to change the private, public IP address also while switching to ISPs?
Because every ISP has some range of public IPs allocated to him itself.
Yes. So can I say that suppose earlier, now usually it's not the case. Suppose I can say, like, suppose a phone company is there, and if you are, now it's not the case, don't think of now public IP, let us take it as your number, phone number. So if you switch like your provider, your ISP, suppose the phone company, and if you switch your provider, service provider, you usually get new number. Though now it's like I can say there is a scheme that, okay, you can change the company without changing the number. Usually it used to happen that, okay, when I'm going to change the company, from I'm switching the service provider, I have to change my phone number as well. So the same case is here as well. When I have to switch from ISPs, like before I was getting from ISP1. So ISP1 has, as you are saying that, as you said, that they assign a public IP pool, public IP address. So suppose they assign this was the earlier IP address, and now you switch to, this was suppose ISP A. Now you switch to ISP B. Now IP pool here is like 198.51.100.x. So you can basically have anything within this pool, but this range is basically now different. So you have to change this IP address. But the benefit is, even this is changed, for them the source is changed, but the source here is the public address, not the private address. The private address remains the same. That is what you explained in easier words as well. Is it clear to everyone? Should we proceed? The benefit, is it clear? Migration between ISPs?
Yes, ma'am.
Yes, ma'am.
So the other thing comes is IP masquerading. Can someone tell me what is IP masquerading? Yes.
So basically, it means that multiple like private IPs are mapped to a single public IP.
How private? Can you tell multiple private IPs are mapped to single public IP? Yes, absolutely.
So yes, so for the outside internet, it would look as if it is just one device, but there are maybe multiple, like 10, 15 or something.
So, what he's trying to say is that single public IP address is mapped to multiple hosts. What does the statement mean is, what we can say that there is a single public address, but multiple host it is referring to, or the rather than saying multiple host, multiple private addresses. So how is it possible? Earlier we learned that one private address mapped to one public address, and then it is sent to the destination part. Now we are saying multiple private addresses mapping to single public address. So how can you tell me how now it is possible? Yes, the concept is okay, that okay, this multiple private IP addresses are mapped to single public IP address. How? Basically through port based NAT. Is the lecture getting recorded? Can someone see, is the lecture getting recorded?
Yes, ma'am.
Okay. Thank you. So yes, as Aman has mentioned in the chat as well. So using the PNATs, or I can say port-based NATs. So how using the port-based NATs, basically now we are using port address as well as the IP address. From I think beginning of the lecture, I'm telling you what is the difference between ports and IP addresses. Can someone tell me again?
A port is something which our process or program access. So, for example, a machine can have, or application OS can have, I think, 256 ports, or maybe. So that means, suppose let us say in organization I have 100 systems. When I send a mail, my mail is attached to a port. Okay. So my colleague's email is attached to a different port number. So that is how internally it gets distinguished. But whereas when it goes to outside, it goes only as a single IP address packet.
Basically, to identify network, we need IP address, but to identify a process, as you said, we need a port number. So yes. Now we are trying to say is, suppose I have a private IP address. And this is its port number, suppose. And this is the other private IP address of the other machine. And the port number here. This is the IP and this is the port number. Now, instead of mapping to different public IP addresses, what I'm trying to do is I'm mapping to the same like public IP. Only what I'm doing is I'm changing the ports. So with that, I'm again saving the IP addresses. Can I say? So same here the public IP addresses are used. So this is what we called as IP masquerading. That single public IP address is mapped to multiple private addresses or multiple hosts. So it supports more number of users, I can say, with a limited number of IP address again. Only the port number is different. We are using the same public IP. So that's why here we call it as, I can say this is process to process communication, because here we are identifying the IP as well as the port number, or its extension of NAT, which is called as port-based NAT. Clear?
Madam, in that case, the number of machines we can have internally is limited by the number of ports in our public IP address.
Number of machines. I didn't get your question.
So the number of hosts we can have internally in our private network is limited by how many port numbers we have in our public IP address. Am I correct? So how many we can have? For example,
it's not that all the organization will use the same public address. I'm getting your point. You are saying that, okay, we'll use same public address and we'll change the port numbers only. With that, there's an issue that all the number of port numbers is the maximum amount of the it's the max amount of the machines we can have in the organization. That is what you are trying to say.
Yes, yes.
It's not that all the organization will have the same public IP address, or we can have multiple as well. This is one way of reducing the number of public IP addresses. I'm not saying all the organization will have the same public IP address. We are just having an example here. Like, we can have, to reduce the number of public IP addresses, we can have the port based NAT also. It's not that only we'll use only one public IP address. We can use multiple, but to save those, we can have the multiple port numbers. Got my point?
Okay, okay.
Next is load balancing. Of servers. We have to be quick because I have to cover QoS, quality of service, also today. So yes, load balancing of servers. Can someone tell me in short what is this? Come on.
Same idea. Like, we are basic, because at the NAT box all the public requests come, so we can move it to different hosts as like basically balance the loads. We can distribute the requests.
Yes. So basically, when the request is coming to public IP address, it can, rather than mapping it to one private address, I can say it can map into multiple private addresses, like 10.1.0.2, 10.1.0.3, multiple private addresses, basically to distribute the load here. So when a request is coming to one to one destination, here we are mapping it to multiple destination. Why we are doing it? To balance the load here. That is what is the main motive of that. Now it has one thing that one question was there. Can okay, if the connection is initiated from this side, with the organization side, it's fine. If the connection is initiated from the receiver, like suppose here the organization has the private IP address, the public IP address, it is mapped to it by the NAT. Now here this is some other device or some other organization. Now can I say here it's device number 2. The device number 2, if wants to connect with the device number 1, what does it need? Can you tell me? How can I connect? If this machine is not initiating a connection, device 2 is initiating the connection. Now what is the, how can we connect it?
It will go through the public address first, then
it should go through the public IP address. But can I say it should? The problem is that this device too should should know about the public IP address of that organization, of this of this private IP. When it is mapped to some public IP, it should know about this public IP address.
Yes, ma'am.
So this is the problem. Now, if the machine wants to send the message, it needs to know the public IP of that. That is the problem. But though I'll not go in that detail, here we use the DNS and all. you know about DNS, the host name and conversion and all. So basically, in order to get the IP addresses of that, that is something else. Just an overview of this I was going to give, I was giving you. So any doubt in NAT? Let's have a quick overview again for the NAT thing, and let's quickly switch to IPv6 and complete this IP addressing. So we saw that there were limitations with the IPv4 addressing. Okay. That's why we, because the limited address space and all, that's why we switched to network, like not switch to, it's a solution, network address translation. What's the solution? Like we can have private addresses also. And in order to reuse the addresses, we can have the public IP address, which are which will be visible to the destination, and private IP addresses which will be used in the organization itself. And as one of you asked, it can be used for like it can be as it is secure as well, because obviously the private IP address is not visible. So every machine is having one private address, but all of them are not operating at the same time. So I can say they can we have not the same amount of public addresses as well. We have lesser number of public addresses because all are not operating at the same time. So it will map to the public address and send it to the destination. So destination can see public IP address. Now we saw that migration between ISPs, it's beneficial there as well, because here when I'm migrating from one ISP to other ISP, obviously I don't need to change the private IP address. I need to change only the public IP address, I can say. Now then we came to the IP masquerading concept. Here what we saw that, okay, again, to reduce the number of addressing rather public addresses, rather than saying that, okay, like we can map multiple private addresses to one public IP addresses with the help of the port numbers here. Then another concept is, another application is load balancing. So if I have so much of load, so much of work from the destination side to this organization, so when it is received to one public IP address, rather than mapping it to one private IP address, I'm mapping it to multiple private address. That is how I'm basically distributing the load here. And yes, one issue that I told you, though it is resolved using the DNS link. Clear? NAT concept? I hope so it's clear. Now coming to IPv6. So now again, I'll switch to shortcomings of IPv4. Can someone now again tell me about the IPv4 shortcomings we have discussed in the starting of the lecture only? Though I have discussed many, it was not required also there. I discussed for IPv6 as well, though it was not required. Now, can you tell me? Only 32 bits in IPv4, absolutely correct. The yes, Nilanjan, you have raised your hand. Yes.
Ma'am, I have one question with the previous one, that you said that the destination 2 needs to know the public address of the destination 1. So, ma'am, how is this then solved if it does not know the destination 1's public address? Does it know the private address, but private address is kind of like is not public. So how is it transferring the data?
That is what I'm saying. Okay, as you said that, okay, I need to know the public IP address. I know the private IP, but I can't send it to it because I have to send it to public IP address. This is your question?
Yes, ma'am.
Now, you know about DNS. What is the use of DNS? When we are typing www.google.com, we know the host name. Then it is converting into private IP. It is converting into the IP addresses. So DNS main motive is to convert the host name to IP addresses. Can I say? So here, can I resolve rather than knowing through the IP addresses? If I know the host name, I can get the IP address, the public IP. They'll automatically map it to public IP and give it to me, rather than simply mapping it. Rather than sending it to IP address, I can tell them the host name, and then DNS will work and tell me the public IP address of that.
Yes, ma'am.
Does it make sense?
Yes, ma'am.
I answered your question. Is it fine now?
Yes, ma'am.
Yes. As Aman has told, the shortcoming of IPv4, small address space, only 32 bits in IPv4. What else? I told you in the starting of the
Ma'am,
lecture.
the length of the header is also limited.
The same thing. Okay, address space.
Okay.
Can I say the other can be the mobility factor as well? So they are unmanageable, though they are now also IPv4 is there, but we have I can say IPv4 typically don't support mobile applications. I told you at the starting of the lecture only. Initially, when IPv4 was designed, it was designed for standard desktop computers, which were fixed. It doesn't require mobility support. They were unaware. They can't imagine also that devices will be mobile in nature. So that's why with IPv4 addresses we are unable to manage it. We have mobile IPv4, the other type, through which mobile IP, the variant of IPv4 addresses through which we are managing. But in IPv6 we have inbuilt that. And if I talk about security authentication, at that time when it was built, there was not that much of issue of security and authentication as well, because at that time, obviously, I can say there were, as I have told you, there were not so many of devices, I'll say, which were using internet there, and only the internet was designed for, I'll say, military applications only. But as the time grew up, the devices basically exponentially they have grown up. So that's why now, as we have discussed initially also in the lecture, that more than one or two devices every person is carrying, and moreover IoTs are also there, Internet of Things, where sensor devices are also there. In the coming future you'll see that everywhere, obviously now also you are seeing that everywhere we have the sensors, like in washing machines, smart lights, ACs, everywhere we are having the obviously they are operated by the internet, and we need huge amount of addresses as well. So that's why the total addresses are limited, I'll say, which can support this global usage. The main shortcoming was this address space. The other one I can say about mobility. The other is the security authentication. Earlier they were not bothered about it. The main motive of them while creating IPv4 was the connectivity thing, not about they were not bothered about the security and uh, like uh, security and authentication. The next is QoS also, which we'll study in today's lecture. So this is today's lecture only, though I'll come in detail about this quality of service. Earlier, obviously, like now I'm doing this Zoom live video. Obviously, earlier there was no live real time service there. So that's why QoS real time support system, it is not that much properly managed by the IPv4. That's why we came up with the IPv6, though in some devices it's not compatible. Like I'll come to that. And that is all. Major traffic is now of the multimedia only, I'll say. So that much traffic was also not there because of this multimedia things, because no one has imagined at that time, I'll say. Now coming to IPv6, I'll say, obviously the first major thing is that larger address space rather than 32. We have 128-bit addresses. We have hierarchical addressing. Can you tell me about hierarchical addressing? Though I have discussed in classful addressing, I'll say earlier also in the addressing techniques. Like, can you tell me?
Madam, in IPv4 also the same thing, right? Class A, Class B, that is also hierarchical addressing.
Yes, you're absolutely correct. in IPv4 also we have classful hierarchical addressing. What is hierarchical addressing? Just by looking the prefix, I'll get to know from which class it's belonging to. It's a hierarchy is maintained there, but we switched from in IPv4 we switched from classful to classless. There the global hierarchy, I'll say, that is broken when I'm going to subnetting, supernetting, and then I'll say from with the private IPs by NAT, again the hierarchy is gone there in IPv4, but here hierarchical addressing we are maintaining. They're only in classful addressing, I'll say, but after that hierarchy is not there. So here we are maintaining the hierarchy. Here hierarchical addressing is there, and I'll come to this optimized routing table when we'll do the routing.
That means, madam, practically 2 to the power of 128 devices we can have, right, to be given public IP addresses theoretically. To the power of 128. So that is so huge number. I think every device deserves a public IP address, actually speaking.
Yes. We can have now we have some I'll say we can have 2 power 128 unique addresses. Theoretically, we can say that. So obviously, it's, I'll say, very huge, massive addresses we can have, and no need for NAT also with so many of addressing. I'll say that also, because globally you can have unique IP addresses so many, so we can bonus is that need of NAT can also be removed, because you don't have shortcomings of IP addresses there. As IPv4 address space was small, that's why we needed the NAT basically to to reuse the addresses, but here we don't have that shortcoming.
Okay.
So because scalability is so much, so no need for NAT and all. Okay, where was I? So obviously, and one more thing, the security thing is also there. Authentication, encryption. QoS, quality of service. I'll come to this only in today's lecture only, and compatibility with IPv4. Because some devices are using IPv4, some are using IPv6, so it has to be compatible with IPv4 basically. So that is the thing. Now coming to IPv6 header format. So other things are same. We have basically mandatory header, I'll say, and extension header. 128-bit source address and destination address is there. Then we have in header the main things I'm telling. Next header, which tells us the multiple optional headers, and hop limit. How many hops should packet traverse to reach the destination? That is there. This is basically the mandatory header. Coming to the extension header, we have the parameters like hop by hop options. So whenever the packet traverses in each hop, how that packet will be treated, that is told by this. Then we have the parameters like routing information. These are all the extension, like all the source like routing information is there. Obviously the source routing, in which route packet should be traversed and all. Then authentication data and all. Then fragment ID. These are all the parameters. I'm not going into detail. When I'll say the packet is fragmented into multiple fragments, then the fragmenting information, I'll say, it is given by this fragment information or fragment ID. Coming to the main thing, though I'm not going in detail with this, IPv6 addressing. Let's see that. So here, as we have told that 128-bit addresses are there. It is represented by 8 hexadecimal numbers. And as we have seen in IPv4, it was separated by dots. Here it is separated by colons. And one more thing is there, if we have all zeros, suppose here 1, 2, 3, 4, we can denote with 1 0 here, which means that which means that all zeros mean which means that this is containing all 4 zeros here. Now if I have, suppose, successive zeros here, then I can replace it by the double colon, which means that it is having successive zeros, and I can count that and then come to know that how many successive zeros were there. Suppose this was the example used there in the presentation. So I can use it once only. Can someone tell me why I can use this double colon once only? Yes, come on.
Because if we use it more than once, then it may create some kind of confusion, like whether we are using for any other addressing or not. If any other address is hidden
Wait.
in those columns.
Basically, if I'll use more than once, then I'll unable to know how many zeros are there, because here I'm not mentioning 3 1 2 3 4 1 2 3 4 12 zeros are there. I'm not mentioning here, but but how I got to know is because it is having 8 hexadecimal numbers. 1 2 3 4 and 5. 1 2 3 4 5 5 hexadecimal numbers are there, and I know 8 are there. So 8 minus 5, I'll know 3, which means 3 into 4, 12 zeros will be there. But if I'll use more than once, then I'll not know the number of zeros. How many number of zeros are there? Does it make sense?
Yes.
It will be difficult to find how many zeros are there. So that is there. And again, I'll not go with. So we have some reserve like IP addresses as well for older network protocols, I'll say, which can be mapped into IPv6 for interoperability, like IPX. It is basically a network protocol used in netware systems, which was earlier used. This is a type of netware is basically a type of OS. It was earlier used, but now it's not used. Similarly, NSAP. This was OSI addressing scheme for network endpoints. So basically, some address space allocation is there basically for so that we can older network protocols can be mapped into IPv6. It's just for that purpose. Now coming into main thing, neighbor discovery. Before going to neighbor discovery, can someone tell me about ARP? Oh, I think in the last lectures, they'll discuss about ARP. Anyone knows about ARP? We'll discuss further in lectures. I think last lecture we'll discuss maybe. I saw that the lecture was discussing ARP. Yes. Can someone tell me what is this?
ARP
Now it
is
is address resolution protocol.
Can you explain further, like address resolution protocol?
so it maps IP addresses to your MAC or hardware addresses.
So basically what we do is, if I want to communicate with some device, I know the IP address of that device. I broadcast the IP address. So I'll tell in short only because we'll discuss further. So I'll broadcast this IP address and ask whose IP address is this? Whose IP is this? And whosoever IP is this, what is the MAC address of that device? Then this is the ARP like request I'll send, then the ARP reply will be there. This is basically broadcasted, and then the ARP reply will be there, though I'll not discuss in detail. That will be basically unicast only, the MAC address. obviously you'll say that again the security issues and all obviously persist there. I'm also working with this only ERP spoofing and all. So what is happening is, like, I want to know about the MAC address of the device. So I'm broadcasting the IP address of the device. I know the IP address, and then with the IP address, basically, I'm broadcasting it. I'll get to know about the MAC address. That device, basically, when it will receive that IP address, it will check with its IP address. It will match it. Okay, it's my IP address, and it will reply back, and that will be the unicast message. That is my MAC address. So basically, mapping from IP to MAC, it is done by the ARP, address resolution protocol. Clear? Should we proceed? Don't worry if it's not clear also, though we'll discuss in further detail. You got the somewhat intuition behind it?
Yes, yes.
So now can you tell me about ICMP? What is the use of ICMP, Neighbor Discovery Protocol, ICMP6? The same thing when we are doing with the IPv6, that is basically ICMPv6 basically. So what what we are doing here also, we know the IP addresses, and this was in IPv4. Now here we are doing in IPv6. A knows the IP address, needs to find the MAC address, and that is like we are doing it through this neighbor discovery. Can someone tell me how? What is the difference between this ARP and ICMP, neighbor discovery? How it is improvement? Like, okay, IPv4 was also doing this neighbor discovery, ICMPv6 is also doing. Like, maybe you have ARP was not discussed in the lecture, but ICMP is just was discussed. Can you tell me any idea? Okay. Someone has any idea about ICMPv6? Yes, yes, come on. Basically, how it is improving, as I told you that I gave you a hint also. Here we are broadcasting, so there is security issues as well. But in ICMPv6, here we are only multicasting to the relevant nodes. To the so basically here we are only multicasting to the relevant nodes. What we think that these nodes can be having this MAC IP address. So that is, we are here multicasting, not broadcasting, only to the relevant nodes, not to the whole network, in order to find the MAC address of that. That is the improvement. Rather than broadcasting, we are only multicasting here. So the same thing, the sender is sending to multicasting message, whose IP is this, and the reply is there. This is my IP address, and if the device is not it is as I told, it is multicasted. Again, if the reply is not heard from the neighbor for some time, it sends network solicitation message. If the neighbor is alive, it will send the network advertisement message, and if there is no response, an unreachable message will be we'll say that it is unreachable. You got the idea, or I should further?
Ma'am, relevant node means it will be in a particular network setting, or will it multicast to different networks as well?
Basically to the neighbors. That's why its name is Neighbor Discovery Protocol. Neighbor Discovery, I'll say.
Remember, what is the range of the neighbor? Like, how do we know?
I think it's basically network. Maybe I have to also see about that. Like how many neighbors? Yes.
Maybe
yes.
neighbors means within the local area network.
Yes. We can say that within the local area network also.
Okay, so under the same network.
Okay. So let's proceed.
Now, I think there is one way. So we will not ask hosts outside our subnet for during neighbor discovery. So that makes sense.
Yes, maybe I have to check because I'm also not sure about, like, you're saying that okay, you will not go outside your subnet.
Because that is not even accessible, right?
But okay, you're saying outside the network it's not accessible also. Then what's okay? Yes, it makes sense. Like, though I'll also check once that what does this neighbor refers to? How many neighbors, or it's about subnet part, or how? Wait, let me check. Maybe I'll check now only. Okay, I think neighbor solicitation is to one, but one neighbor only. But here, then how it's multicasting? Only one target neighbor. Okay. Mm. Okay, maybe I'll read about this. How? Because I'm also confused. Here we are reading that it's multicasting, but network solicitation here means that neighbor solicit, like here means that okay, we are only like sending it to one target neighbor, and then if I talk about router solicitation, that means that all the routers which are there that it is sending to. And if I talk about neighbor solicitation, that means that only one target neighbor we are sending it to. But then the question is why we are saying it's multicasting. Multicasting means the target, multiple sets of neighbors we are sending it to. Maybe I'll check like what does neighbor here means. How many neighbors? That is the question. No? Maybe I'll check this and I'll clear the doubt in the next lecture. The other concept is clear. Like. About IPv6, like instead, apart from this neighbor thing. Yes, or anyone has the idea about this neighbor thing? How many neighbors? Because network solicitation means, wait a second, the destination address. Okay, I'll check it and I'll inform you.
Ma'am, I think because even in the same network, because as we are maybe not knowing the particular address, so it is kind of like sending multicasting to the relevant nodes, and the one who is responsible will respond because we do not know the MAC address of the data link layer. That's why.
Yes, that is fine, that okay, like we are multicasting it, and whosoever is having the same IP address for that person will respond. Yes, okay, like I'm multicasting the IP addresses, and I'm asking whose MAC is this, and the person who's having that MAC basically will respond to that. But how many I'm multicasting? Here I'm not broadcasting. In ARP I was broadcasting to whole network, but here I'm multicasting to intended nodes only. And what are these intended nodes? Are that only to the one relevant node? But again, we are saying multicasting, it means multiple nodes. How many nodes we are multicasting it? And how we know, the question is how we know that these are the relevant nodes in the network, not the other ones.
Yes, ma'am. Same question.
So maybe in the next lecture I'll look about this. I also now only this question rise to my mind. Also, I'll look on this thing, and any one of you also I'll also suggest you to look upon this, like how many nodes, how many target nodes, how we'll get to know about the relevant nodes. Then we'll discuss in the starting of the next lecture only. I think Nilanjan, you were there in socket programming class, na?
Yes, ma'am.
I have left with the homework problem, but last time no one was there who has attended socket programming, that while loop. Maybe we'll discuss in the end of the lecture. Like homework, or I was asking you why that while loop is there. Okay, you remember that?
No, ma'am, not exactly.
Yeah, I'll come to that afterwards. Maybe in revision class, I'll ask. Okay. So now one more thing is there. IPv6 also supports. Now this was the feature that okay, I don't have to broadcast it. I have to only multicast it. Though I'll check about this neighbor thing also. And the other thing was that addressing obviously spaces so much that now we don't require also NAT devices and all. Mobility support is there now. The other thing is we can migrate from IPv4 to IPv6. We have something like dual stack implementation. Like it is supporting IPv4 also devices, and like devices are supporting IPv4 also and IPv6 also. Single machine supporting both of them. So we have that also. And the other thing is like tunneling also we have like address translation. Can someone tell me about that address translation quickly? Come on. So basically, I'll say that I can convert from IPv4 addresses to IPv6 address also. If I have, suppose I have received from IPv4 the device which was having the IPv4 to IPv6, I can convert from the decimal to hexadecimal by appending all ones there. And here in IPv6, basically, if I want to convert from IPv6 to IPv4, that is also possible by taking low order 32 bits only. Rather than taking everything, only I'll take this 32 bits, the first 32 bits, and I'll say that this is IPv4 address. Is it clear, the IPv6 thing? If you'll have the doubt here, you can ask me in the next class only. As we have lesser time, I have to cover about this QOS also. I hope so. These things will be clear only once you'll go through it. Not a huge issue as well.
Madam, one difference is in IPv4 we have 4 decimal digits, correct? And in IPv6 we have 8 hexadecimal.
Yes, absolutely correct. That's why we are having 128 bit and 32 bit.
And once right now IPv6 is not rolled out, I think it is only IPv4, right, all over the world?
Yes, but some devices are switching to IPv6 as well.
Okay. So once IPv6 is rolled out across thing, that means each mobile phone can have a unique IP address?
Yes, obviously NAT will not be there, but still IPv4 devices will also be operatable, I'll say. Again, it will not be disappeared at all.
Okay. Okay, madam.
Okay. So about now QoS, quality of service. As we have discussed in the discussed now only, that we have now many multimedia streaming applications also, like I'll say YouTube, Netflix and Hotstar and all. Rather than having simple file transfers as we were having before, we are not only transferring the bits at the other end, or combining at the other end all the bits and reconstructing it. We have many multimedia application, YouTube streaming, and videos and all, everything is there. For that, I can say that maintaining quality of service is much needed, because if suppose video data is transferred simultaneously, we are playing the video, whenever I'll say internet quality is poor, you usually see the buffering thing, video gets stuck. For that thing, obviously QoS is essentially needed for us, I'll say. So what is client expecting from the internet? Client is expecting that I should see the continuous stream of video without rebuffering. So now the question arises, what quality of the service should be provided for the smooth video streaming? Network needs to provide more services. If your video is buffering, I'll say you need more bandwidth and all. You have to pay more for the internet connection, I'll say, to the network service provider, so that congestion shouldn't be there. Can I say that? We learned about congestion control there, or I'll say congestion avoidance there in TCP. You remember that? What was the protocol which we used and everything? Can someone tell me? What was the main idea? Yes, come on. Am I audible?
Yes. So the idea was to adjust the window size.
Adjust the window size.
So, like, if there was congestion, you reduce the sending rate, the sending window.
AIMD. Yes, absolutely correct. Or window size. Yes. So what we were trying to do is we tried to control it by reducing the sending rate of the sender if the congestion, once the congestion is detected. So we were trying to avoid congestion. So can I say that TCP congestion control is enough? Yes. We don't need congestion control here. Then if TCP is enough, congestion control.
Madam, congestion is related to bandwidth, right? How it is related to IPv6, IPv4?
No. IPv6 topic is completed now. Now I have come to quality of service.
Okay. Okay, madam.
Maybe I'm rushing today because lot of syllabus is left. So the addressing schemes I have done. This IPv4, IPv6 is done. Now we have come to the another topic, that is internet QoS, that is quality of service. Now in quality of the service, I'm saying that okay, now we have real-time services as well. Though I'll come, we can relate with IPv4, IPv6 also. Okay, that's the other thing. Now can I say that TCP congestion control was enough? It avoids but not finds the help to solve congestion.
Madam, the reason that we don't use a TCP congestion control for streaming videos is because it's a lot of overhead, and it reduces the effective bandwidth because of the retransmit and the TCP congestion control. So that's why we use UDP, which doesn't have any of these protocol, right? UDP just blindly sends it, and even if something is missed because of its video, we can look over. I think that's what I understand. Yeah.
What are the other people's view? What are the others view about this? What he's trying to say about UDP and TCP? What others want to say? Yes, Nilanjan, Aman, yes.
TCP cannot handle the quality like the buffering and the jittering and all.
Yes, in one sense you are also correct. If I talk about TCP only also rather than UDP, okay, UDP, that is a different thing, that UDP don't have any congestion control. If I talk about TCP also, TCP itself cannot handle all those things, because TCP is, once the congestion is there, then it can reduce the sending rate. But to avoid the congestion, then we should go in, we should go more further, like jittering and all. I'll come to that. So how does congestion is impacting the network performance? Let's see, and how this is not helping us. TCP congestion.
Maybe at a higher order layers, we have to do congestion control rather than at TCP level. Maybe at a sessions layer or applications layer.
I'll come to that. Don't worry. I mean to say that TCP basically is helping us in congestion control once the congestion is detected. Once the congestion is there, TCP detector try to control it by reducing the sending rate, as one of you have told me. Now, but still what about if before the congestion only we have to reduce the we have to totally avoid it? How we can do it? Let us now see in this lecture. And how does congestion impact the network performance? By bandwidth, it impacts the bandwidth, it impacts delay, jitter, as well as packet loss. So let's see what is the bandwidth. Can you tell me how, what is bandwidth first of all?
It's a number of bits per second, the effective rate of data transfer.
So basically amount of data that is transferred over a fixed amount of time. I can say that. So some applications, obviously, they are bandwidth hungry, I'll say. They have, we have low capacity channel. So better to go for, I'll say, if I talk about an user level space, better to improve the bandwidth. For improving the bandwidth, go for better subscription with the network service provider. Basically, this is the bandwidth thing. If I have to, one of the parameter for the congestion which impact the network performance. If we are having the congestion, obviously the bandwidth will be impacted there. Now, can you tell me about the delay?
Delay is delay in receiving end, transmission delay. Okay.
Yes, I'll come to that. So basically, packet needs to wait more basically to in the receiving end. So I have the sender, suppose I have the receiver, as one of you have mentioned about transmission delay. Let's see that. So we have three types of delay: transmission delay, propagation delay, as well as queuing delay. So can someone of you tell me about what are these in very quickly in two lines? What is this?
Transmission delay is the overall one, which is equivalent to propagation delay plus queuing delay.
No. I think you are getting confused. What about others?
What's the question?
What is transmission delay? What is propagation delay? And what is queuing delay?
Now, transmission delay is for to transmit all the packets across the channel.
Basically, to push all the packets in the network, that is basically transmission delay.
Yes, ma'am.
The data into the pipe, I'll say.
Propagation is movement of the data end to end.
So basically, moving it from end to end, that is the propagation delay. Can I say it depends on the length here because it is moving?
Yes.
And
yes.
What about a transmission delay? It depends on capacity of the channel. Can I say?
Yes, ma'am.
And bandwidth.
Yes. And the other one is queuing delay. Can you tell me about that?
It is related to the buffers on the sender and receiver side.
Yes, basically it's related to buffer queuing delay on the sender and the receiver side. So this is the delay, and queuing delay basically dominates sometimes the transmission plus the propagation delay as well. And it's a major delay, I'll say, basically. And because the packets are getting in the queue, if we have a fixed capacity there at the other end, packets are getting into the queue and they have to it is basically how much we have to wait, and increasing the queue delay impacts is having a major impact on the congestion as well, I'll say. In other words, these were the type of delays. Understood? Now coming to jitter. Can any one of you tell me what is jitter?
Madam, jitter means there is a delay, no doubt, but if the delay is consistent, for example, there is a 0.1 second delay, and if it is consistent across the data stream, then we say no jitter. But the delay is say sometimes 0.1, sometimes 0.2, sometimes no delay. So that means you get a flicker in the video. Okay.
Yes.
So
Absolutely.
if it is a consistent, that is acceptable, even though there is an offset, but the viewing experience is good. There is no jitter. Yeah.
Absolutely correct. So suppose I have source, destination. These are the routers. Here, if I'll say different packets, there are the sequence of packets, and suppose different packets are having different delays. Here, one packet is reaching this time, one packet maximum delay is suppose 15 millisecond. Different packets, they are experiencing different level of congestion in the network, I'll say. And if I'm having different delay, I'll have the problem, a lot of problem, basically in the applications like live streaming as well, when I have to transfer immediately, because as you told that there'll be a lot of flicker, there'll be a lot of disturbance. Sometimes the quality is very good, and sometimes we are waiting for the next video frame, then immediately we are getting the frame because data from the server is not coming, I'll say, in the constant rate. There are a lot of ups and downs, I'll say, in other words. So that is basically, we call it as jitter, the variation in end-to-end delay. Now, what is loss?
Loss means outright missing the packets. The dropping of the packets due to choking at congestion buffers or overflowing buffers.
Though theoretically we say the loss would be generally zero, but if we talk about practically, it's not possible. We usually have the minimal loss because in the wireless networks, because of interference and all, there are certain factors as well.
Madam, in a pure TCP protocol, there is no scope for loss, right?
There can be, that is what we were discussing. There can be still be a congestion, though. When I'm talking about congestion also, then that is what I was trying to explain earlier, that once the congestion is detected, then we are trying to reduce the rate of the sender. Once the congestion is detected, which means that there can be loss as well. Packet loss can be there. Okay, you're saying again we can send the acknowledgement and all those things.
Yeah, we can have large buffers, and then
what are the other people's views about this? Yes, come on. So yes, in TCP packet loss happen, but I can say that packet loss do happen, but I can say TCP detects it by the sequencing and all, sequence number, acknowledgement and all, and that's why we say it as TCP is reliable. So because I can't say it prevents doesn't prevent the packet loss. I can say it can detect it and recover it automatically. So that's why we say it as I'll say reliable. It have packet loss, but it uses acknowledgements, retransmission, congestion control, all of them for the reliable delivery.
Yeah, actually by definition, TCP should never lose packets.
TCP do lose packets, but it's reliable. Why we say? Because again, you might have seen like we are using their. If it doesn't lose packets, then why we are doing that acknowledgement thing and all
no,
those?
No, it loses, but it retransmits. I'm talking about end-to-end effective loss.
Yes, absolutely correct. Yes, TCP can have packet loss, but it uses acknowledgement, retransmission, congestion control in order to have the reliable delivery. Okay, let's proceed. So these were the primary QoS parameters: bandwidth, jitter, loss, and delay. Now coming to classes based on QoS. Application classes based on QoS. So we have basically here divided the classes. I'll come to that, why we have divided it not. We have like constant bit rate, like voice over internet, voice over IP. What's that? Can someone tell me?
Yeah, voice over IP is basically digitized voice over packet network. So
Can I say WhatsApp call?
Yeah, WhatsApp call is voice over IP.
Yes. So basically we have the applications, so we have divided into that. So one is constant bitrate, voice over IP comes here, real time variable bitrate. So like video conferencing, um, that comes in real time variable bitrate, then non real time variable bitrate. I'll come to all these classes, don't worry. And best effort, available or best effort. So basically, if I talk about this, we have maximum, we give my maximum priority over voice over IP. That is there. Constant streaming of bits is there, I'll say. If I talk about real time variable bitrate, which is video conferencing and all, it means that in this class, it has to be transferred within this much of delay, otherwise it will be failure. Obviously, because it's real time. Non-real time, we can say there can be a loose bound on packet loss and available bitrate, like suppose a simple file transfer. So whatever the best effort is there, we can have that. So we'll now discuss about these classes. We'll again just come to these classes, don't worry. First, we'll discuss about basic QoS architecture. I'll again come to these classes.
Ma'am, there is a streaming one also. So
Which one?
streaming as a class.
Stream. Oh, video streaming and all.
Yes. So which one of these is video streaming? Third?
Video streaming is third, non-real time variable bitrate.
Oh, okay.
That's the same only. So coming to basic QoS architecture. First, we have admission control. Can someone tell me what is admission control? Admission control is that it ensures that new flows are entered into the network only. If I say the QoS of the existing flow along with the new flows can be satisfied. I know you didn't get anything. I'll come to it. Simple, I'll talk about the telephone network. When you call someone, there's a message like we hear in that, like all lines are busy, please dial after some time and all, which means, what does it mean? It's pretty common when we are calling. What does it mean? The network is not allowing new flow because all network resources are blocked here. I'll say here, not allowing new flows here. If all network resources are blocked. Can I say?
Yes, ma'am.
So, basically, all network flow, here, all network resources are blocked in servicing the existing flows, basically based on the QoS requirement. So that's why they are not allowing the new flow here. So admission control is it helps in ensuring that whether the new flow can enter the network or not. So that is why when we are calling, what is happening? That the resources are already blocked, the person is busy, you can't connect to that, because that they're not allowing us to connect to them because the resources are blocked there. The new flow is not allowed to enter into the network. The second is classification and marking. Can someone tell me about classification and marking? Yes, come on.
Ma'am, it classifies and categorizes the traffic. I mean, the network based on the IP address and the protocol and the SLAs.
Not based on IP address. Suppose if I have, again, I'll come to this. Suppose I have this, I want to have a video call. So it will have it will be, I'll be in the real time variable bitrate class. So it will mark the packet, which packet requirement, which is it a constant bitrate class. So basically it will classify me into these classes, basically classify the packet into them, basically mark the packet. So or I can say which packet is mapped to which class here. Is it CBR or is it another class? Or is it real-time variable bitrate, non-real-time, or available or best rate? So basically, the classification marking main motive is to mark the packet which class it belongs to. Is it clear?
Yes,
Should
ma'am.
we proceed? Now the third is policing and markdown. Can someone tell me about this? I'll give you the same example. It was discussed in the class as well. Suppose this is the source. This is the router network, and this is the destination. These are the intermediate network. The packet here moves from here to this router, but router here finds out that suppose this packet. Okay. One more thing here. There is a service level agreement, or I'll say here the quality of the service. Here it's like we can have, according to the application, we can have only 10 millisecond of end-to-end delay. That is the requirement of the application. If you will not have 10 millisecond end-to-end delay, then it's of no use. You can have max of 10 millisecond of the delay. Now the router finds out that this packet has already experienced 9 millisecond of delay. And it's impossible, this router finds out that this packet has already experienced here 9 millisecond, and within one remaining millisecond, I have to transfer it to the destination. And it's obviously impossible. Can I say that? And as it cannot satisfy QoS, quality of service, so sending it with the more delay, it's basically useless. Again, it will it will block the whole link, take bandwidth. Again, the application will need to process it again, or if refragment and all, everything, sequencing and all, everything will happen. And rather than doing everything and then again dropping it, it's better to drop it now only, because in intermediate stage only it knows that okay, this packet will not be will not reach in time. And if it will not reach in time according to it's better to drop that packet. So basically this should I'll say policing and markdown, these are the certain kind of flows when it is seeing it's seeing that what is the policy and how it have to behave, like whether it should drop down the packet, whether it should basically forward the packet and all. You got this concept? What was someone has written in the chat. Okay, we have written earlier only. Anyone, can you explain policing and markdown again, so that I should know that you got the concept? Yes, come on.
We check if like basically we drop the packets for which we cannot satisfy the QoS.
Basically it is it will check about the policies and all, and if policies markdown, policies violating, so it will take a certain decision whether to forward it or whether to drop it. The other one is scheduling. It's like prioritizing the packets. So suppose here, I'll have the different queues as well. So first priority is given to the red queue, second is given to the black queue, and the third is given to the suppose to the third queue. Why these priorities are given?
Because of the classes, Q application class, the QoS classes.
So according to the application, we have basically divided into classes. So suppose the class is basically real time and the other is file transfer. So obviously we'll give the priority to the real time video streaming rather than real time video rather than to the file transfer. That is how we are giving the priority, and we are basically scheduling. So what we are doing is we are first transferring the packets which are in the red queue, though we'll come to the scheduling in detail. So we are basically transferring the packets from the red queue. Then if red queue is empty, then only we'll go to the black queue packets, and if black is empty, then we'll go to the red queue. Red queue, then black queue, and then yellow queue, and again then to the red queue. Though we'll come to all the scheduling in detail, all these things in detail. Okay. One more thing, policing. I think everything is cleared, maybe. Traffic shaping. Now coming to traffic shaping. Okay, one more thing, maybe I forgot. I wanted to give you example. Okay, rather than giving the example, can you tell me what is uplink, what is downlink? It was used in the lecture as well. It was used in the lecture. Am I correct? So in the lecture, they have said that okay, uplink is suppose the data maybe of the uplink is different and the data provided for the downlink.
Yes, madam. For example, in Netflix, there is a more of downlink rather than uplink because we don't transfer much from our TVs to server, and all the time it's only from server to our TV.
So basically, server to client and client to server. Can I say?
Yeah.
So server to client, what is that?
That will be highest because it is streaming bandwidth.
That is downlink. Can I say?
That is downlink. Yes.
So basically, from network to your device, that is downlink.
Yes.
I just wanted to tell everyone so that if anyone is having a doubt, so because I haven't used these terminologies, I think maybe someone, if they don't know, downlink is basically from network to device, your own device, and this is uplink is from your device to the network. Suppose you are uploading a file, that is basically down uplink, and as he has told that if you're streaming the video or you're downloading a file, that is basically uplink.
Madam, I would say rather than calling network, call it server.
Because server, yes.
Is a downlink.
Absolutely correct. So now coming to traffic shaping, can someone tell me about traffic shaping? Yes, come on.
The name itself indicates self-explanatory. It says adjusting the speed as per the limitations and the dynamics. I don't know. Yeah.
In other words, I can say we have learned about jitter. It reduces the jitter, I'll say.
Yes. So reducing the overall speed so that the jitter is minimized.
So that we can have basically the output traffic shaping is output traffic should have constant packet rate, which means it is reducing the jitter here. So if I talk about the difference between policing, I'll again come to policing, as we saw that okay, suppose I have the network like this. What will policing do? Because policing is like you have to send like the traffic till this amount only. This is policing is ensuring it. So what will policing do? Policing will only send the packet till this traffic only. That is what, otherwise it will drop it. That is, it was trying to do it. Now shaping, as we know, it is reducing the jitter, which means it should have in, we should send it in the constant rate, which means it will send it constant packet rate smoothly. So this is basically shaping. Any doubts? Basically here we are smoothing out the entire rate in shaping. What we are doing there, so here additional packets which are not basically confirmed, which are violating the QoS, we are basically dropping them. Is it clear? Should we proceed? Yes, come on.
Yes, ma'am.
Now we have algorithms as well, leaky bucket and token control. Let's discuss in short. What is leaky bucket? Can someone tell me?
It is a technique for like your shaping of your traffic, right?
So basically it's traffic policing and shaping, a technique there. Can you explain the technique?
So basically we model it as if there is a bucket with a hole and water constantly like drips out that bucket.
And okay, we are pouring the water in the bucket.
There is
And
a capacity of the bucket, and
what if the bucket is full?
so more water overflows. So basically we reject the extra buckets, so to say.
So if it's full, obviously it overflows, which means we reject the extra packets, as well as they are coming, output is at the constant rate because we have to do the shaping. If you are exceeding this much of capacity, then you drop out or delete, or I'll say drop the additional packets here. And size of the hole, what does it indicates? That it indicates that constant rate the outputs are coming here. That is what it means there. If I talk about again the same thing, how it is doing. So it was, suppose, our network. So if it was more than the rate, basically it will first of all it is coming in the constant rate, so that is why the shaping is there. Policing, again, if it was more than that, then it will drop it if the queue is full. Though it is little different from the shaping because it's not totally like this, I'll say, but again related to that only. Now can you tell me about what is token bucket? Yes.
We have a token generator that works parallelly. So, and there is a bucket that fills all those tokens. We use it for things like burst and all that.
So basically token bucket, it supports traffic burst. So idea is like, suppose what is scheduler here doing? This is scheduler. Suppose if there is a token, take out the token, and like we are basically, suppose there was like packets were not sent at that time, but we are here filling the tokens here. And suppose I'll say that 10 packets, suppose 10 packets are there, like 6 tokens are filled because earlier no packets were sent, but the tokens were getting added. Now when 10 packets arrived, the 6 packets, I'll transfer it at one flow only. I'll not go by one like a leaky bucket at a constant rate. I'll send 6 packets because earlier I'll say that there were no packets at that time. The token were getting filled, So this bursty data, we can basically send it. That is what is the main concept here. You got the concept, everyone? Though maybe the differences and all we'll discuss in the last lecture. I have in the next lecture. I have to go now. So again, the scheduling part and all, I think it's left. So any doubts in today's lecture? Yes, come on.
No, ma'am.
What about others? I hope so. The lecture is clear. Any feedback? How was the lecture today? Though I think I was a bit quick, but otherwise the syllabus, again, I thought that today QOS will be completed again. Left. Lecture was good. What about others? Any
Okay,
feedback?
madam. Okay, good.
Okay. So let's meet in the next lecture next Tuesday. Okay. Thank you, class.
Thank you, madam.